Thanks to the audience.
Okay, so we'll start today's colloquium. The speaker is Yang Wang, and he's a visiting faculty member in the Anne and H.J. Smead Aerospace Engineering Sciences Department at CU Boulder. And that's where he earned his PhD in 2021. And he has been there since. And his research focuses on GNSS receiver signal processing and the use of spaceborne GNSS measurements for remote sensing of the Earth's ionosphere, atmosphere, and surface. So please go ahead.
Thank you, Nick. And thank you, Nick and Don, for the invitation. It's an honor to be here to share some spacewise related work here. And my research primarily focuses on GNSS navigation and as well as using the signal for remote sensing. So it's not just for the ionosphere, and it's also for the Earth's surface, the low atmosphere, as well as the ionosphere. So this is the how I got connected to space weather. This is through using a different new type of GNSS measurements for the ionosphere observation from the LEO satellites. So for today's presentation, here's a brief outline. So I start with the introduction of GNSS observation of the ionosphere TC. I'm sure most of you are familiar with this part, so I'll just be very quick for this. Then that is followed by an introduction to the overlapping geometries between GNSS radial occultation and refractions. So this is very interesting overlapping geometries. So I would like to highlight this part.
I'm sorry,
Yes.
I missed the explanation of what GNSS stands for.
Okay, I have one slide for it just right after this.
Navigation satellite system.
It's a global navigation satellite system, including the global position system of the US.
Okay,
Then, so I will include both radial occultation and reflectometry, but the talk will more focus on refraction signal. And I will introduce the coherent refraction, which is for GNSS signals reflecting off relatively smooth surfaces, where we can have the carrier phase measurements, which is a precise range measurement, can be used for precise navigation, as well as precise remote sensing, including the ionosphere total electron content. So with these kind of GNSS refraction and radial occultation measurements of the ionosphere, there are some potential uses of these measurements, including this ionosphere TC mapping and this precise observation of the ionosphere plasma structures and the ionosphere disturbance detection. So I would discuss these potential use of these kind of measurements. So the first introduction topic is GNSS, the Global Navigation Satellite Systems. I'm sure most of you are familiar with this. So be quick. The things I wanted to emphasize is that right now we have over 130 GNSS satellites in the medium Earth orbit or geosynchronous Earth orbit. And each satellite, it transmits either dual frequency or multiple frequency signals. Then for the ionosphere observation, the estimation of the ionosphere parameters, primarily this total electron content, is based on this frequency dispersion of these impacts on different frequency signals. Then as a navigation system, GNSS, it naturally provides these very precise range measurements from carrier phase, as well as these relatively coarse but absolute range measurements from pseudo range. And it provides these very precise and accurate orbits and clock solutions, making it not only a precise navigation system and also a remote sensing system, including the remote sensing of the ionosphere. So the estimation of the ionosphere parameter, here we particularly refer this total electron content from this GNSS signal measurement that is based on these ionosphere impacts to the GNSS signal. And this impacts is proportional to the total electron content and is inversely proportional to frequency square. So the frequency is a radio signal frequency. Here the total electron content is defined as the total number of electrons along the signal propagation path. So here we have this simple signal propagation path as this red arrow. And along this propagation path, the signal propagates through the ionosphere. Then this total electron content is the total number of electrons along this signal array with an area of 1 meter square, and this column following the signal path. Then this additional delay or the phase advance to these signal measurements is proportional to the total electron content along the signal propagation range. And this estimation is based on this simplified Appleton-Hartree equation, which is the reflective index of radio wave in plasma. And the assumption is made for that the ionosphere impacts is primarily this first order term here. And based on this, we have this ionosphere delay to the radio signal to be proportional to this total electron content and inversely proportional to this frequency square. And this is the simple equation and used by all these GNSS receivers that produce ionosphere TEC measurements. Then the ionosphere total electron content measurement is along the signal propagation path. So it's along the signal path in various geometries. So it can be described by this elevation angle. So we have this or incidence angle. So the angle from the receiver to this GPS satellite can be of various angles. And when we describe the ionosphere total electron content, it's more convenient to use this vertical total electron content to produce this two-dimensional map. Then that requires a conversion from this slant direction to this vertical direction. So that is done through this mapping function, and which normally uses a geometric mapping function. So it's basically the ratio between the zenith distance from the top to the bottom of the ionosphere divided by the propagation range of the signal within this ionosphere. Then both the transmitter from the satellite and the receiver, they have different hardware biases, and those biases have to be corrected before we can use this range difference term, this ρ2 plus minus ρ1, which is the range difference between L1 and L2 GNSS range measurements. Before we can use this range difference to do this ionosphere TEC estimation, we have to account for the differential code biases, which is a hardware bias between the L1 and L2 range measurements. And they exist in both the transmitter side and the receiver side. And after accounting for this.
Quick question. What's the typical temporal resolution of these measurements?
So the typical temporal resolution of GNSS measurements depends on the receiver. So this ionosphere monitoring receiver, they tend to have high rate, 100 hertz or 50 hertz. But for typical navigation receivers, they typically just have 1 hertz output.
Wow.
So most of the receivers, they use this dual frequency or multiple frequency range difference to get the slant TEC and follow this geometric map to convert that to vertical TEC. And we can use a network of thousands or even tens of thousands GNSS receivers to map the global ionosphere vertical total electron content. So on the right is a map of vertical TEC using thousands of GNSS receivers. And this data are available from the symmetrical database. So here we see clear structures of the ionosphere total electron content. And we also see large areas we don't have measurements. So these areas are because we don't have GNSS receivers deployed in those regions, those inaccessible terrain areas, as well as the ocean areas and polar areas. And the motivation of this work are using LEO satellite-based measurements to observe the ionosphere is to fill some of the observational voids over ocean and ice using this radiation geometry as well as the refraction geometry. So here's an illustration of these two geometries. So for radiation, and we talk about the radiation on board LEO satellites. So we have the GNSS receiver on board a LEO satellite and receives the GNSS signal from the direction that is close to the Earth's limb. So the signal is propagation through the ionosphere and sometimes the atmosphere through a relatively low elevation angle or the gradient angle. And simultaneously, there is a reflection signal that is from the same pair of GNSS and LEO satellite geometry. Then they share the same advantages. So the major advantage is that is the passive nature of GNSS receivers. So the GNSS receiver, it does not transmit any signal, so it just receive and process the signal. That makes it relatively low cost and low power consumption. So that is suitable for small satellite or even CubeSat deployments. Then that makes it relatively low cost to have a large constellation. We can talk about tens or even over 100 small satellites, CubeSats, of GNSS receivers that provide high temporal resolution observation of the Earth and Earth environment, including the ionosphere observation. So here we have one example, the private company called Spire Global. They used to have up to 20-something CubeSats for rate calculation, then they adjusted some of their satellites to also collect these gradient angle reflection signals. Their original intention is to use the reflection signals to map the sea ice. Then using those data, we demonstrate that we can use the same signal designed or purposed for the sea ice observation. We can also use that for the atmosphere and ionosphere observation. Then we can compare the LEO satellite measurements, the GNSS measurements, versus these ground-based GNSS measurements. They have a lot of commonalities. So we are processing the same signal and using the similar methods. All these geophysical parameters, they are extracted from signal parameters, including the signal power, then the pseudo range, and the carrier phase. So the pseudo range is what we normally use for navigation. If you say that your phone has a navigation accuracy of 1 or 3 meters, then that is using the pseudo range. But for some precise GNSS receivers achieving centimeter accuracy, that is using the carrier phase. So the carrier phase is very precise, but it's relative range measurements, which means it does not provide any absolute magnitude. So normally we use these carrier phase to be aligned to the pseudo range absolute magnitudes to have this smooth carrier phase based pseudo range. And we can use that for both the navigation and remote sensing. So here we can use these dual frequency or multiple frequency range measurements from either pseudo range or carrier phase. We can use that to estimate slant TC. Just based on how this slant TC is defined and how it is estimated, it's not sensitive to this geometry. As long as the signal is propagating through the ionosphere and the signal has good quality, which means that the carrier phase and pseudo range can be accurately estimated, then using the range difference, we can estimate the slant TC along the signal propagation path, regardless how far the signal has propagated, whether there is a refraction or reflection. And the estimated slant TC corresponds to all the total electron content that is along the signal propagation path. So here for this rate occultation geometry, then the slant TC is corresponding to this segment within the ionosphere. Then for the refraction, that is corresponding to the summation of this segment and this segment. Then the differences between the LEO satellite GNSS measurement and the ground-based measurement, I have this summary here. The first difference is in geometry. And the geometry makes it more complicated to retrieve higher order data products from these LEO satellite-based GNSS measurements in both rate occultation and refraction. I'll have more details for that. Then the second difference is the receiver motion. For most of the GNSS ground receivers, they are static, or even if they are moving on a vehicle or even on aircraft, the velocity is not comparable to the LEO satellite. So for the LEO satellite-based measurements, the satellite is moving at 7.7 something kilometer per second. So it's very fast. It's faster, much faster than any ionosphere structure propagation velocities, most of them. So that is an advantage to observe for example, large scale structures. If we have a large scale structures like the tunnel ionization, which spans over 1,000 kilometers, it's not possible for any individual GNSS receiver to have the entire observation of this structure. But it's possible for LEO satellite to take just a few minutes to fly across this region.
Sorry, what did you call the structure?
Tunnel ionization. It's a very large ionosphere enhancement structure that is spanning from like 60 something degree latitude to the pole.
And it's called what again?
Tunnel ionization.
POI.
Tongue of oh, interesting. Okay.
Or polar patches. Some
Polar
polar
patches.
patches are also very big.
Yeah, yeah.
Mhm.
So I got a question, maybe
Yes.
the technique about the carrier phase.
Mhm.
I try to recall what I learned from my graduate school. But sounds like that should have like a uncertainty range of 1 period. Is that
So that is ambiguity.
ambiguity?
So the carrier phase for GNSS signal in L-band, the carrier signal wavelength is about 20 centimeters.
Mhm.
And it's relative, which means that it's difficult or sometimes impossible to have this integer number of how many cycles
Mhm.
using this range measurement based on carrier phase. So so one thing we need to be careful with processing the signal is keep it continuous, which means you cannot jump from one cycle to the other cycle. As long as it's continuous, then we can use them to estimate the slant TEC following this equation. And that is a relative TEC because it's N1 and N2 here. They are the ambiguity integer terms, and they cannot be estimated. But in most cases, the absolute N1 and N2, they cannot be estimated.
So basically, it's a combination of the pseudo range and the carrier phase that you can get a.
Yes, for most of the receivers, the high precision range output are the combination of carrier phase and pseudo range. Then the last term is noise level. So for this direct signal from GNSS to these ground receivers, the signal to noise ratio is normally very high, unless there is a scintillation event. Otherwise, the signal is very clean with high signal to noise ratio, low phase noise, a low phase noise level. So we can get this range at the precision of sometimes 1 millimeter precision is possible. But for this refraction signal, the refraction is causing this degradation of signal to noise ratio, as well as some multipass impacts to the signal range measurements. So that increases the noise level. So we will see that this can cause some limitation to use these LEO satellite-based measurements for this ionosphere observation, for example, for this ionosphere scintillation detection. So here's a bit more introduction of these radiocultation measurements. So here, the description of this radiocultation geometry is usually using this straight line tangent point height, which is the height of the signal ray to the nearest point on the Earth's surface. Then the radiocultation measurements can be used to retrieve the slant TEC, then this electron density profile under some assumption, primarily this spherical symmetry assumption used in the Abel transformation to get the electron density profiles, as well as the scintillation indices. So for the scintillation indices, it's pretty similar to how this, for example, this S4 index is very similar to how S4 index is calculated for the ground-based measurements. So here, the estimation method has the major similarity, but when we do the analysis, we can see the difference in this power law frequency range. I'll have more details just in a few minutes. So for these electron density profiles, which are the mostly used GNSS radiocultation ionosphere product, and that is of relatively low horizontal resolution because of this spherical symmetry assumption. So that assumption is made for example, if we have this electron density estimated for this area, so that assumes that over here for this area it has the same electron density, so that can span over 1,000 kilometers. So that leads to the relatively low horizontal resolution from these rate fluctuation measurements. Then let's do a comparison of this geometry between this rate fluctuation and refraction. We can see that horizontally, these refraction measurements is more sensitive to these horizontal variations, while this rate fluctuation is more sensitive to these vertical variations. So these two types of measurements, they have complementary geometries. And their geometries are highly overlapped. So here I'm showing one example from a single set of data. So this bluish color line is showing the straight line tangent point height. So here we have this range from over 500 kilometers, which is close to the orbit height, to minus 200 kilometers, which is for the lower atmosphere observation because of the bending from the lower atmosphere. For ionosphere observation, the range of this straight line tangent point height is from about like 70, 80 kilometers to the orbit height. So that is corresponding to roughly this range. And if you look at the horizontal track, the occultation track, that is corresponding to this segment. And in the meanwhile, we have the refraction signal, which is reflected from the ocean surface at an elevation angle range. The elevation angle is defined as this angle. So that is the dashed line is the horizon. Then this arrow is pointing from the refraction point to the GPS satellite or the receiver satellite. So in the meanwhile, the signal is reflected from the Earth surface in the elevation angle range from about 2-3 degrees to about 7-8 degrees. So within this segment, whenever there's a occultation event, for this occultation height from about 100 kilometers to a few hundred kilometers, there's always a corresponding refraction signal that is available to the receiver, but has never been intentionally processed by any of the existing occultation missions, such as Cosmic, Cosmic 2, and even Spire. So Spire Global, they are conducting two separate missions, one for occultation and the other is for refraction, because when they record the refraction signal, they have a cutoff frequency of 5 to 30 degrees. So they only record signal for the elevation angle within 5 to 30 degrees. That means there is a pretty long distance of useful refraction signal that are very useful for atmosphere and ionosphere observation that is not collected by existing system. That is spanning from 0 degree to 5 degree. So is about 1,000 kilometers spanning horizontally. So we can use these measurements to get the horizontal gradients of the ionosphere as well as the lower atmosphere. Then for this refraction, not all the segments, all the signal measurements are useful. The carrier phase measurement is only from these high quality coherent refraction signal measurements. So that means the high quality means that the refraction is of high coherence, which means that the signal, the carrier phase is highly concentrated and it can be estimated with relatively high signal to noise ratio and low phase noise. In that condition, we can have these continuous carrier phase based range measurements. Then we use these range measurements in the bottom two panels to estimate the range difference between L1 and L2 signals and use that to estimate the slant TEC. Then the coherent refraction is available for refractions over relatively smooth surfaces, and those surfaces include ice surfaces, ocean surface when there is low wind speed, and even if there is relatively high wind speed like 7 to 10 meters per second, if the refraction angle is low enough, the signal can still be coherent reflected. Then for most of the surface water, like inland water body, rivers, lakes, and wetlands, they have smooth surfaces and can coherently reflect the signal to provide the reflected signal phase measurements. So here's one example of this Antarctica area in August. So that is a local winter. So there is a high sea ice coverage in the southern hemisphere. So most of the sea ice surface, they tend to be smooth enough to coherently reflect the signal. That means that the reflection signal over these sea ice areas can be used to provide the ionosphere measurements. So we can use those measurements to fill the data gaps in the South Pole areas. So here this color is representing the coherence metric, which is developed to quantify the coherence level. So the higher coherence metric indicates the more coherent reflection from those areas. So we can see most of the sea ice is a good coherent reflector, and some areas in the ice interior, the ice sheet interior, they can also coherent reflect the signal. Then even over ocean, we have seen that at very low elevation angles. So here, this segment of measurements is reflected over this ocean area, and from elevation angle from 1 point something degree to about 7 degrees. And here we have this wind speed up to 10 meters per second. That is corresponding to 1 to 2 degree elevation angle. And we have this high signal to noise ratio and the circular lens as this phase coherence indicator. So we have good phase measurements under this 10 meters per second wind at very low elevation angles. So that validates that we can use this low elevation angle reflection over even relatively rough ocean surface to fill the data gap over ocean for the ionosphere observation. And again, this kind of geometry, there is no operational data collection for these low elevation angles below 5 degrees. But this shows good potential that we can use these measurements to help fill the data gaps over ocean and over ice. And here is the GNSS reflectometry geometry for the Ionosphere TC observation. So here we have the signal transmitted by the GNSS satellite. It propagates through the ionosphere and reaches the Earth's surface and gets reflected and exits the Earth's atmosphere again. So there's 2 points of signal propagation within the ionosphere. One is for the instance rate and the other for the refraction rate. And for the LEO satellite orbit height is usually 500-600 kilometers, which is within the ionosphere, but is above the majority of the total electron content or the plasma in the ionosphere. So when we do this mapping, we do need to account for this above orbit partial total electron content for this reflection path. Then overall, from the reflection geometry and the reflected signal, we get the direct measurement of this total electron content along this reflection path. This slant total electron content for the reflection path, it equals to the summation of this instance rate portion, STC1, and this reflection portion, STC2. So for any individual track, it's not possible to separate this contribution from this reflected signal measurement. But if we have a large and densely covered reflection tracks, we can formulate a mapping problem to somewhat separate this contribution to produce these mapping results for those regions. Or if one of these tracks is within an area, we have good coverage by the ground receivers, we can interpolate the TEC using ground mapping results for one of the tracks to get the estimation of the other track. So here's one, yes.
So I'm trying to understand what's the meaning of these two slant TC addition. So is that equivalent to like the vertical TC at a certain path, or so how to interpret STCR on the left?
So STCR is the total number of electrons along the signal propagation path, which is highlighted by this red color within the ionosphere.
Yeah, I understand, but what about when you add up the two slant TC, 1 and 2, they are from different directions, right?
Yes,
And
they are along the same signal propagation path. Their impacts to the signal is the impacts to signal. They formulate a joint impact to the measurement. So when we have this ionosphere delay to the reflected signal, that is contributed by these two areas, and we cannot separate their contributions.
so that's like the signal goes from the GNSS satellite and then reflected out of the ground.
Mhm.
Okay, and you're comparing that to the STCD, or
No, not comparing. It's just illustration of geometry. So the receiver is ionosphere. It receives signals from all directions as long as you have antennas facing towards those directions.
Oh.
So for any receiver in the ionosphere in the low Earth orbit, it receives multiple direct signals, and it can also receive multiple reflected signals. And this receiver is moving at very high speeds, like 7.7 kilometers per second. So that is driving this signal rates to also moving at very high speeds. Then for convenience, we abstract these measurements as these IPP points, these ionosphere pierce points. The IPP1 for this instance ray track, and IPP2 for this refraction ray segment. So when the satellite moves, it drives these 3 points to also move at kilometers per second. The 3 points are the IPP1, IPP2, and the refraction point.
Right.
So we will see that for a segment of the refraction signal, we have 3 tracks. One is the IPP1 track for the instance ray. Then the spectral point track is on the surface. Then the IPP2 track is close to the receiver and is at the IPP height, usually 300 to 400 kilometers. And the velocity, the spectral point velocity is about 5 kilometers per second. Then IPP2, because it's very close to the LEO satellite, is moving at a velocity that is very close to the LEO satellite, like 7 kilometers per second. So here, within 3 minutes, we can produce these horizontal gradients of the summation of IPV1 and IPV2 to be this red curve from the reflected signal estimation using carrier phase. So we have very high precision. So if you look at there's no filtering to this measurement. So if you look at the noise level, is like 1 centimeter or 2 centimeter or so. It's highly precise and producing this very high fine scale observation of these TC variations. And the black line is interpolated results from this global TC map under some assumptions like the total electron, the IPP height and the compensation for this above orbit portion of this partial TC. Then the validation shows that, first of all, the 2 of them have consistent trends. So that is a good sign that we are showing good agreement with this global ionosphere TC map. Then the other is the fine scale observation of TC variations. So this is just one example. There are some more interesting structures from the ionosphere that can be used for the study of ionosphere plasma structures, as well as this quantification of these variation impacts to GNSS navigation services, etc. And the validation of these can be combined with this Earth science application of Earth surface oximetry. So the Earth surface oximetry, if you want to have the centimeter accuracy retrieval of the Earth surface, we have to accurately correct the ionosphere impacts. And these impacts is proportional to the total electron content. So that we can use that as a validation to show that the ionosphere total electron content we extracted as this variation curve is indeed what the impact that ionosphere has caused to the signal. So if we use the estimated red curve in the previous slide to correct for the ionosphere impacts in the altimetry retrieval, we can get this red line, which is very consistent with the ocean surface model. And if we use the GIM for this correction, we get this backline, which is about a meter deviated from the model. And the mean sea surface and ocean tide model is very accurate. We usually use like several centimeters or up to 10 centimeters to describe this accuracy. Then here's one slide showing the data coverage. So data is not useful if it does not provide a very high density coverage. So within one day in 2021, on May 12th, the first column is showing the ground track, which is the spectral point track, and the color is representing the signal to noise ratio. So we can see that and then the gray shade is representing the sea ice coverage. So we can see that most of the reflection over sea ice, they have strong returns, high signal to noise ratio, meaning it is coherent, and we can use those segments to retrieve the total electron content. Then the other two columns are showing the IPv1 and IPv2 tracks. So here we can see that the non-coherent segments dropped from these two columns. So here we are only showing these coherent and usable segments in both these northern and southern hemisphere high latitudes. So we can see that the spatial coverage goes to about 60 or a bit lower than 60, 50, 55 degrees latitudes in both hemispheres. So it's providing precise total electron content measurements, the horizontal gradients for these regions. Then here's one slide summarizing the signal processing of these measurements. So it's actually pretty troublesome to process these signals because the reflecting signal, the signal is weak, and partially because the signal is the hardware is not designed to receive this reflected signal, and the antenna gain is not high enough to produce these measurements with low enough phase noise. So here we have a mix of rough surface reflection, the incoherence, and the large noise due to this insufficient antenna gain. So we have large phase noise. Then we need to do first the detection of useful phase measurements, then use these useful measurements to do the retrieval. So here we have developed a method to quantify this coherence level that is based on this low frequency component power within these phase measurements. So if that is noise, that is corresponding to kind of uniform noise spectrum. Then if that is low frequency component, then the signal power is, or the data power is, the spectrum power is more concentrated at low frequency. We use that to quantify the coherence level to detect the useful segments. So for example, we have one track that is over a lake and a very large lake. So we also have a wave on the lake surface causing this rough surface and low reflection coherence. So we can detect these scattered segments of coherent and useful phase measurements. Then we can either drop those measurements or we can find a way to connect those measurements by solving this relative phase ambiguity between those segments. And we can have a relatively long segment of continuous phase measurements for either the Earth surface retrieval or the ionosphere retrieval. Then because of the weak signal, and we just had a question about this ambiguity and cycle sleeps, when the phase noise is comparable to the wavelengths or half the wavelengths, it's very easy to have these cycle sleeps for the measurements jump from one cycle to other cycles. And we have also developed methods called the simultaneous carrier cycle sleep and noise filtering method that is applied to this reflection signal to mitigate those cycle sleeps. So this method is effective. So I have one example of using several hundred of GNSS tracks to map the mean surface elevation of the lake. And this is showing a very good results and is using several hundred tracks. So that indicates that this method is effective in processing relatively large amount of data. We have successfully processed about 1,000 tracks, and here are showing about 600 out of these 1,000 tracks. But it's still a few steps to be able to have this real operational capability to process a large amount of data, especially for sea ice and for ISGs when the surface is not well characterized and is changing. It's difficult to have a reliable method to massively process a large amount of data. Then, if we can successfully recover these clear phase cycle slips, we can have this continuous and high precision slant TC. But in order to convert slant TC to vertical TC, we need the absolute magnitude, because the conversion is based on this geometric mapping function. So if we don't have this accurate estimation of these absolute magnitudes, then there will be a bias introduced to it when we convert it to vertical TC. So we do need vertical TC, the absolute TC, to be estimated for this reflection signal TC measurements. And that is pretty challenging for existing data, because the hardware bias is difficult to characterize. So each satellite has one navigation receiver and navigation antenna, and also 2 sets of reflectometry antennas. So there are different channels to process the reflectometry and reflection signal and the direct signal for navigation. So those different channels, they have different hardware biases. So here's a simple calculation of the hardware biases between those navigation channel and science channel. And for this front reflectometry L1 and L2, they the blue and red color respectively, they show pretty stable bias. But for the other set of antennas, the back reflectometry L1 and L2, they exhibit very large variations within the range from 0 to 10 meters, and that is corresponding to about 100 TCU, so that is not acceptable. Then for this back reflectometry, it's very difficult to produce any absolute measurements, so we can only have these relative measurements, the relative slant TC from the carrier phase only. It's not possible to have this absolute TC measurement from pseudo range. Then when we use it, we can either just use these horizontal gradients characteristics of these measurements, or we can introduce an unknown variable to add this absolute value and solve it in a mapping problem. So the potential use of these GNSS reflectometry and reflection measurements. So I'm going to discuss 3 potential uses. One of it is ionospheric TC mapping, and we see those blank areas in both these hemispheres and in lots of these ocean areas. And we try to fill some of the data gap by integrating these LEO satellite TC measurements into this mapping problem. So here is some preliminary results from a new mapping method. So in the new mapping method, we formulate a least square estimation problem for the grid points of this vertical TC with a 1 degree resolution or grid size. Then we use this line of sight slant TC from Madrigal database as input, as well as the slant TC from reflectometry. And we plan to use a reflected slant TC as well, but it's not added to these results shown here. Then the assumption we made in this mapping problem is that we trust the normalized electron density profiles from this IP simulation. So instead of using this geometric mapping function, we use these normalized electron density profiles as the reference to convert the slant TC to vertical TC, or just use that in the mapping process. So here in these preliminary results, we have this medical database vertical TC map on the left. Then we use this new method to reconstruct the mapping results using only this slant TC from medical database. We see some improved data spatial coverage because we use some measurements that is only partially propagating through some ionosphere areas, and we use that to estimate the total electron content. And we also see some slight improvement by integrating these recalculation measurements in expanding this data coverage.
This IPE simulation.
This the IPE is IPE, this ionosphere plasmasphere electro dynamics. So I think it's just for this March for March 2023 storm.
Yeah, so
Yes.
so this plot is based on 30 minutes
Yes.
experiments. Okay.
Yeah. Is based on 30 minutes measurements, and within 30 minutes, we have some refracted signal measurements. So here the black lines are showing these IPv1 and IPv2 tracks. I didn't use different colors to distinguish these two tracks, just to show this data coverage. So within half an hour, in some good half an hours, we have relatively dense coverage by the refraction signal. For example, this 8:30 to 9 on March 23rd. And for some of the segments, we have much fewer refraction tracks. Then we hope that by integrating those refraction signal measurements, we can further improve the data coverage of TC mapping in these polar regions. Then the second use of these measurements is the study of ionosphere plasma structures. So these GNSS reflectometry tracks, they are more sensitive to the horizontal variations and the recalculation geometries, and we can use that to observe the total electron content variations as the signal cuts through ionosphere structures. So here's one structure, and we don't know where it is. So these large variation from these reflection signal measurements, it can be from either IPv1 or IPv2. So it's possible we find the data source from these ground receivers to show that in IPv1 region, we don't have large variation of TC. Then we can conclude that those variations are contributed by this IPv2 track closer to the North Pole. Then these are very large variations, and this can explain those large phase variation in the GNSS measurements in high latitudes when there is a so-called phase scintillation. And those measurements can be used to characterize or establish or characterize the relationship between the TC gradients and the impacts to the navigation service, to the position accuracy, and these impacts from this ionosphere. And we have also seen some interesting measurements of the horizontal gradients as the signal cuts through the polar patch structure. So here's one major polar patch. We can see it from this magical TC map that the peak TC is about 4 or 5 times higher than the background. So it's a very prominent polar patch structure. And as the reflected signal, the IPv2 and IPv1 and 2 tracks cuts through these ionosphere regions. So here we believe that these large gradients are from this IPv2 track, which is a longer track that is on top of this patch structure. So here, bottom to top, we see the TC variation of about 30 TC units. And surprisingly, this patch structure is producing very smooth gradients. If you look at this relatively low frequency component from this TC estimation. And just surprisingly smooth. And about 15 minutes later, the polar patch was broken into a few pieces. So the color is not that obvious, but probably can still see it. The original polar patch is more like one piece is broken into a few pieces. And another reflected signal track, still this IPv2 track is cutting through this patches area, and we see a very deep diffraction between these two pieces of polar patches, and still the gradients of this slant TEC are very smooth. But it's difficult to tell that if any region of these polar patches are causing scintillation, because the scintillation impacts, they are quantified by this disturbance, which is a random term. So, and the magnitude can be very small, can be on the order of centimeters. So here the noise level is too high to directly observe any scintillation from these slant TEC measurements. Even though it's possible that based on the structure, the properties of what we see as slant TEC here, we can try to characterize the relationship between the shapes, the gradients of the slant TEC and the physical processes that cause that, and if that physical processes can cause any scintillation impacts, but that is not directional, not a direct approach. Then we do have some direct observation of the ionosphere scintillation from occultation and refraction geometries. So here I'm showing one example of a occultation and reflectometry event. So it's still a joint event. As long as it's a occultation event and the area is over ocean, there's a high chance that there is a good reflection track, a reflection signal can be picked up to retrieve the ionosphere. So here is the black line is the LEO satellite orbit, and the two magenta colors showing the IPP tracks. Then the red, the green track is the tangent point track for the occultation point. Then the blue one is a speckle point track. So we first look at the occultation signal. So the top panel is showing the signal to noise ratio. We see some scintillation pattern here, and we can quantify it as this S4 index. So we see this S4 index going up to almost 1. Then we do this short time Fourier transform of this signal to noise ratio. We see this relatively low frequency component enhancement for this scintillation segment. Then for this reflected signal, because of refraction and the low signal to noise ratio, as well as some potential scattering impacts to the signal, then we see those large fluctuations of the signal to noise ratio. So the scintillation pattern may be hidden under these fluctuations. Then it's not observed by the traditional S4 index. But if you look at the spectrum again, we can see that the lower frequency component, there's an enhancement here only for this segment. And that segment is very close to the spatial location of this scintillation observed by the occultation path. Then if we look at one slice of the spectrum, we can even see this power law pattern of this spectrum of this signal to noise ratio fluctuations, these scintillation impacts. And we also notice that the frequency is much higher than the ground receiver scintillation frequency power law range, which is around 1 Hertz. Here is several Hertz to a bit over 10 Hertz. That is because of the high velocity of the platform is much faster than the ionosphere irregularity structures drift velocity. So here's a short summary. A set of methods have been developed to retrieve ionosphere parameters from individual coherent tracks, and further development still needed to have any operational capability to produce massive amount of data products. And current efforts also focus on the potential use of this data in the TEC mapping and the study and more precise characterization of these ionosphere plasma structures, as well as the detection of ionosphere disturbances. And some references, and the work was supported by a NASA award. And that's all I have. Thank you very much.
Had you any questions?
Yeah, the GNSS signal reflection, have been used for many things. They won't consider the ionosphere effect at all, or they just ignore those. Like, ocean, wave structures and like that. They taking into the ionosphere effect.
For using GNSS as scalerometry for ocean wind retrieval, they don't consider any ionosphere impacts.
You don't think that, okay.
So that means their accuracy is going to be compromised, right?
Under scintillation is possible, yes. The scintillation is so the major mission for ocean wind retrieval using GNSS is thickness. So the thickness product, as far as I know, they don't consider any ionosphere scintillation impacts. But there has been some work using thickness signal power to retrieve S4 as an indicator for ionosphere scintillation. But I think that performance is compromised because the signal, the thickness data is 1 Hertz, so it's much lower frequency than the scintillation frequency for LEO platforms.
Can you go back to your summary slide for a minute?
Yeah.
Oh, yeah.
Yeah, I skipped the, sorry, go ahead.
You mentioned Spire, like operational coherent GNSSR reflectometry data source. Can you get any data from the cosmic satellites?
I wish they do it.
Could be.
They only collect radical measurements. And for any retardation event, there is very likely there's a reflected signal also received by the antenna, but not processed by the receivers.
It would take a receiver processing change to
Yep.
get it. Feasible, possible.
It's feasible. Yeah, I'm trying to convince someone to collect simultaneous radiation and refraction measurements.
They have a limited bandwidth. They have a mission. Maybe occultation, not their mission. Reflection. So,
Yeah, for SPY is the same. The radiation is always a priority, and refraction is secondary. But 2023 is a very good year. So in average, they have 5,000 tracks every day. Then the number has declined a lot this year. They lost some satellites, the solar maximum. Then I don't know, maybe not that interested in investing that much in this data product, so not launching new satellites.
Yeah, I think Spire is, they're trying to shift their business model away from RO to ship tracking or something like that. They're not emphasizing RO as much, as I understand it.
So basically, you're using the GNSS constellation and the ground receiver and the LEO satellites. And that LEO satellites is just the SPY project, or so what kind of LEO satellite can be used?
So so Spire had the LEO satellites carrying their GNSS receivers developed by themselves. So those GNSS receivers, they do this open loop tracking to produce 50 Hertz measurement outputs. So other science, so that is pretty similar to cosmic receivers as well. So it is outputting high rate 50, 100 Hertz output. Other GNSS reflectometry receivers, they output 1 Hertz output, and there is no carrier phase. So there are 2 different kinds of receivers. One for scalerometry, for ocean wind, they produce the delayed Doppler maps, they drop this phase information. Then this rate occultation type of receiver, they are designed for this rate occultation signal, which is strong signal. Then they can also be used to process some strong reflection signal. So they are using the same processing methods and apply to the reflection signals to produce these reflection data products. So it's most likely, to answer your question, the radio occultation receiver. So as long as there is a LEO satellite carrying the radio occultation receiver and with the proper antenna facing towards the appropriate directions, can be used for these applications.
So, okay. I'm curious, like how many such satellites are operating in the space, but you kind of showed the number of tracks. That's
Yeah.
relevant.
So in 2023, I had number of 25 CubeSats from Spy Global for radio occultation. Then they usually only allocate several satellites performing this reflectometry.
There are quite a lot more radio occultation satellite, but not, there are a lot more radio occultation satellite, but not all of them do the
Oh,
reflection.
yeah. I'm still curious about the previous plot of the TOI. That's I think that could be a very novel usage of this technique in some of the space. Maybe this one or the earlier one. You have the 3 plots.
3 plots?
Panels, 3 panels. Yeah,
This one?
like yeah,
Mapping?
right. Yeah, this one.
Yes.
Yeah, because this is like you put the data over the 30 minutes interval together. It's kind of you're assuming like this structure is stationary over this 30 minutes interval, right? Or in other words, this map can be good for studying variability longer than 30 minutes.
Yeah, so 30 minutes is selected for convenience.
Hmm.
So it's using 30 minutes, we can produce these maps with tracks that are not too sparse.
Right, right.
So for some of the structures, I do see the variation faster than 30 minutes. There is significant changes, and it's still difficult. So the GNSS measurements from LEO satellites, they are still relatively too sparse to continuously observe ionosphere structures. They very often hit some very interesting observations, but continuous observation is very difficult at this moment.
You have 2 points, TCs, 2 slash C TCs.
Mhm.
That give you a lot of ambiguity as to which of the leg of the slant TEC is giving the variations. Are you considering like using multiple sampling of the geometry to like combine the multiple sample to determine reduce ambiguities between which leg of the TEC causing your enhancement or anything like deductions, something like that?
Yeah, you mean for the ionosphere disturbance?
That's correct.
So we can also make it a mapping problem. So if there is a track that is showing a very flat, very smooth TC, then we can conclude that in both IPP areas, the ionosphere is quiet. So we can use those tracks to map those quiet ionosphere areas. Then once there is another track that is overlapping with one of these quiet areas, we can conclude that the variation is from the other area. And we can also leverage existing ground measurements as well. So from ground receivers, we see this very low temporal variation of TC. We can predict, or we can estimate the variation to be relatively low in that area. Then that helps.
That's an AI problem.
Yeah, we need to put together a lot of measurements from different sources to use these multi-source measurements for some mapping problem.
One more question, but yeah, feel free to go back up, yeah. Okay. I go back to your last slide. previous slides. Yeah, I can understand with the reconstructed map, how you have better spatial coverage there. But why during some of those kind of enhanced regions, say, or bluish region, looks like it's also changing the value of like from compared with the magical TC map. Is that because of assumption of that simulation? Is it some background model there?
So this is very preliminary work. We just started. Then overall, we don't see significant bias if we take the difference between this original magical TC map and the reconstructed map using this relatively new method. If we look at the difference, we do see some enhancement depressions, but overall it's pretty even. So we don't see any
Yeah, especially
bias
mentions that,
in that.
yeah, that red area looks like it's kind of wider in the reconstructed region or have value. Just wondering about shall we kind of rely on that? Is that reliable or?
Yeah, I had a question too. So for this original vertical TC map, it's pretty narrow. But if you look at the line of sight TC measurements from Madrigal, it's just as wide as the other two maps.
Okay, yeah,
I don't
so
know what
that,
happened to the original 1 degree map.
because it's probably the mapping from geometry from the slant TC to vertical TC, that assumption, I think is probably not.
Yeah, I've heard about Madrigal's IPD height assumptions, but they sometimes use very high IPD,
Yeah, that,
500 kilometers, 550.
yeah.
It's pretty surprising. Those.
Yeah, that's what I'm wondering, if like the reconstructed one would be more reliable or, yeah. Just curious.
Yeah, for this work, the intention was not to develop a new method that can produce better TC maps than Madrigal. So the idea is to establish a framework that can integrate LEO-based measurements.
Fill the gaps,
Yeah.
options, etc.
We cannot directly integrate the radiation refraction measurements into this Madrigal TC map or their mapping results. Their mapping approach uses the mapping functions, and that cannot be applied to
Yeah.
the LEO geometries.
Sure.
We did this comparison out of curiosity and for validation. And we didn't expect to have a better performance than Madrigal
Could.
maps. And we expected to have somewhat comparable performance with existing Madrigal mapping results. And with that framework, we can integrate LEO measurements and fill some of the data gaps. That's the motivation.
Sure. Yeah, another question, if we can go kind of last couple slides where you show the simulation and the short time for this one. You mentioned about like the lower frequency ones probably have more power or corresponds to the highest indices, etc. What is the frequency range when you mentioned that? Because the y-axis cannot see.
Yeah. So here I have, for the reflected signal, I have a spectrum for just this slice. So that is from 0 to 25 hertz, because the data is 50 hertz.
Yeah, but
We can have the spectrum from
where you
0
have the largest power, what is the
largest
frequency
power is, I think it's 3-4 hertz.
for hertz? Okay, so the y-axis actually hertz.
The x-axis is hertz. So this log 10.
Oh,
frequency.
you mean that they are, I mentioned the spectrum.
The y-axis is power.
But on spectral graph, the y-axis is the y-axis, right?
Oh yeah, this is hertz.
Oh, yeah, this one. Okay, so it's a couple of hertz.
Yep.
Okay, I see.
Yeah, I should have frequency there. Then the color represents this correlations from output.
Sure. Yeah, if you can get rid of the pause spectrum and just take a look at the time series S4 indices. I see a lot of variations about tens of seconds from S4 indices. Do you have any physical interpretation of that, or But it won't take.
Just because the signal is weak.
Uh-huh.
Then when we do the correlation in the receiver, and the reflection is not only just the reflection point, some other area can come in, and with relatively close Doppler frequency, and those will be contributing to the noise components in the measurements. So the reflection is introducing noise into the measurements, and the reflection is also degrading the signal power. We have lower signal to noise ratio, and also kind of contributing to the noise or the fluctuations in the signal to noise estimation, and making it relatively low quality measurements, and that increases overall noise flow. So this spectrum plot at the bottom is after subtracting the high frequency noise level from this entire plot.
Focus is being low pass filter already.
No low pass filter is just, so this is showing the power spectrum, and this entire map is after subtracting some values as the mean of these high.
Oh,
frequency components.
subtracting the background.
Yeah, subtracting background, yes.
Okay.
And it was a bit surprising that we still see this power law pattern, which could be a good indicator of this simulation signature.
That's all the question I have.
Okay, well, why don't we stop? So thank you again.
Thank you.
So your finding number is next to mine. Your finding number is 1056. The mine is 55.
Hmm?
Your finding number, the grant number.
Uh-huh.
Yeah,
Okay.
1056. Mine is 1055. Looks so familiar. Thank you.